So while we're opening to page 27, let's just check in again about the projects. How are we doing so far with the projects? Some people making progress? Yeah. Good. All right, keep plugging along. I love that so many people are here early to our class and then working on homework or projects or anything calculus related, so keep it up. We'll take our quick look at the calendar. So today, September the 12th, we have two topics to cover today. The derivative function and then something called differentiability. Again, notice quiz number 1 is approaching. 1 week from today is our very first quiz. I will give you more info about that quiz as we get closer to it. It is on the material for classes 1 through 7. Okay? All right, so that is the calendar. Any questions on the calendar? All right. So then again, back here on the packet, we're on, is it page 27? Yeah. We needed a reader for the daily summary. Let's go to Kyle for the daily summary. Okay, thank you. So number 1 here talks about how last class we defined the derivative of the function to be this expression right here. We have a limit, we've got this fraction called the difference quotient, and remember we saw last class that the derivative was the slope of the tangent line. Repeat with me. The derivative is the slope of the tangent line. The derivative is the slope of the tangent line. Yes, it is. So that's what we saw last class, was that formula. But you can find the derivative at any particular number that you wanted to. And so what we're going to do today is generalize even further and say f with this little apostrophe. Remember, that's the notation for the derivative, and it's read f prime. Instead of thinking of f prime at a particular number, we're going to think of f prime at a general variable, x. And for that function, the x value on the graph is the input. Slope of the tangent line at that point is the output. We'll make that clear with an example in a moment. And so number 2 is our new definition for today. This is the definition of the derivative as a function. What's the only difference between that definition and the derivative we saw last class? Yeah, the specific number a just became a general number x. Okay, so number 3 says, can we take the graph of y equals f of x, which is pictured here on the left, and sketch the graph of f prime of x? The basic idea when graphing a derivative is to plot points of the form x comma slope. So we'll see that right now. So let's take a look at the points on the graph where the curve is flat. Do you guys see, how many points do you see on that curve where the curve is flat? You should see 3. Just put a little dot on each of those 3 points where the curve is flat. If your memory is ridiculously good, you might remember what we called those on the very first class of the semester. Remember you guys had this big table with a bunch of cubic functions in it, and you would count how many times the curve was flat like this? So they were called critical points, and we'll define them formally later. Did you get it? Nice. Okay, so if I'm thinking about drawing tangent lines at each of these 3 points, what's true about those tangent lines? The slope is 0. So I'm going to draw really tiny tangent lines today. But definitely the 3 tangent lines there are horizontal. And so what that means, for example, at this first point, x is, how much is x at that first point? It's -1. We'll just read that from the graph. So x is -1, but the slope of the tangent line is 0. Okay, so that's true at that point. And then we can come up to our next point. We'll have to estimate a little bit here. Roughly x is 1.2-ish. And the slope of that tangent line is 0. And then we've got one more, maybe 3.1. And again, the slope is 0. But remember, we're graphing the derivative as a function. And we know that the derivative is the slope of the tangent line. So if I'm thinking of these green things as being points on the derivative, then the first coordinate is just x. But the second coordinate isn't the y value that you're looking at. It's the slope of the tangent line, which is 0 at that point. So that the points that we're writing here with green coordinates are going to be points that are on the derivative of this graph. Here, how much is the x? 1.2, comma, and then the slope of the tangent line, that's a 0. And then finally 3.1, comma, 0. And those 3 points then come over here onto the graph that we're going to put up here, which is going to be y equals f prime of x, which is the derivative. So negative 1, comma, 0, and 1.2, comma, 0, and about 3.1, comma, 0. Okay, I'm going to pick another point. Let's do this guy in blue. I'm going to pick this point right here where x is negative 2. What do I need to draw in there if I'm thinking about graphing the derivative? I need to draw a tangent line. So let's draw a little tangent line. This is going to be a really rough sketch, so don't even worry about using a straight edge or making it nice and neat. Just a very, very rough tangent line. What's the x coordinate at that blue point? Negative 2. We read that from the graph itself. And now we're just going to estimate, and honestly, I don't even want you counting boxes. Just throw out a number. Negative 6. Super. Negative 4. Super. It's negative and it's fairly big, right? I'll say negative 5. I don't know. Just ballpark. It's okay. So the coordinates of the point we're about to plot over there on our derivative graph are negative 2 and negative 5. And so that comes over here, negative 2, negative 5. So you're plotting the x-coordinate normal, but then the y-coordinate is the slope of the tangent line, because after all, the derivative is the slope of the tangent line. Okay, so let's just do a tiny bit more of this, and then we'll start the activity. For example, right here, no, let's do this guy in blue as well. Okay, what do we need to draw at that blue point? A little tangent line, something like that. How much is the x-coordinate at that point? Definitely 0. Estimate for the slope, maybe 2. Something positive, not quite as big as the negative 6 we had before, right? It's not as steep. If you have a lot of time to count boxes, you can get a more accurate picture, but we're just ballparking here. So that means that, what's the point over on the graph of the derivative? 0, 2, right up there. Okay, and I think that's probably good enough. I'm just going to go ahead and finish up with a rough sketch here. So we had really steep negative tangent lines here, and at some point it turns around. I don't know that it turns around at the point I picked. I'm not saying that, but at some point this curve starts to come downhill again, right? So the tangent lines on this part are all going to be negatively sloped. So that means I got to get down here at some point. So it turns around, I don't know where exactly, and then it comes negative. And then at some point, I think we got to turn around again, because what kind of tangent line slopes do we have here? Positive, so I better get up here to some positive slopes. So something like that. Y equals f prime of x. Okay, so you're going to do a little bit of that. and then some other stuff in the activity. We're going to come back together with about half hour left in class, but see how far you can get. On the next page, there's a part B, which you're going to completely ignore. You can cross that off. Okay. So just do part A and raise the flag if I can help. Okay. At the top of page 32, it's got a vocabulary word. It says a function is said to be differentiable if its derivative, which we saw this new definition today, exists. Function is differentiable if its derivative exists. So you might ask yourself, well, how could the derivative not exist? You just drew a bunch of derivative graphs, right? Like given an original graph, you can estimate the graph of the derivative. You also did some algebra on that square root of x business, so you can just plug in and go through some algebra to try to find a derivative. So how might a derivative not exist? Well, a derivative, as you can see here, is officially, technically, a limit. And there are ways for limits to fail to exist. You guys remember the main way to have a limit not exist? If it's not continuous, right? Like if you had the limit from the left was one number and the limit from the right was another number, then the limit doesn't exist because the limit needs to approach the same number. So here are some ways for a derivative to fail to exist. The first picture you can see is a corner. So let's think about tangent lines here. At this point right here, is the tangent line downhill or uphill? Uphill and pretty shallow, right? Not very steep. And then as we keep moving this way, what happens to the tangent line? It's a little bit steeper. And I'm going to go ahead and go to that guy, like the final point. I'm going to draw the, quote, last tangent line coming from the left-hand side. And maybe it's something like, oh, that's pretty poor. All right, let's try again. Something like that. All right, so there's the last tangent line from the left. But now in another color, I'm going to draw some tangent lines on the right. Is that tangent line uphill or downhill? Downhill and relatively flat. And then this one here is still downhill, but a little bit steeper. And then the, quote, last one from there might be something like that. So if you were thinking about the value of the derivative, maybe the last one over here has a slope of 1. But on the other side, the last one has a slope of maybe -1. So does the limit approach the same number from both sides? And the answer is no. So the derivative doesn't exist at that one point, just at the corner. The derivative at all the other points is totally fine. But a telltale sign for a derivative to fail to exist is a corner, because you're going to have two different values of the slopes as you approach that point. And so the limit would fail to exist. Yeah, I think you're going to get a corner anytime the derivative just has a dramatic change at one point. Yeah, so we can draw another quick diagram here. So like if it looks like that for a little while, and then at that point it decides it's going to like go, you know, like at a different angle per se. Again, it's a corner where the derivative doesn't exist. Okay, middle picture, vertical tangent line. So again, if we're just thinking about tangent lines at various points, some tangent line there, some tangent line here, some really steep tangent line, and then we get to this one magical spot where the tangent line is vertical. Probably only happens at one point in there. But if the tangent line is vertical, then what can you say about its slope? It's infinite or doesn't exist, right? We've talked about vertical lines in previous classes, and we say the slope is undefined. So if the slope of the tangent line is undefined, and the derivative is the slope of the tangent line, and the derivative is undefined there. Okay, and then if I look at this last picture, I see the hole I put in the graph is laughably large, but anyway, there's discontinuity there and a very puny point down below. So what's the problem here? Okay, let's see. So if I'm drawing tangent lines like on this side, you get these, you know, like positive uphill type things, and there's some last tangent line there. But then like the last tangent line on the other side is probably quite similar to the last one we had before. So that's not the problem. The problem is that there's a hole there. And so when you actually do this piece right here, so oftentimes, or last class, this was an f of a, right? It was a particular number. The numbers are too small, I can't read them, but 1, 2, 3, 4, 5, 6. Let's say a is about 6. F of 6 in this problem maybe is 2. Fair enough. But it is nowhere near the f of 6.1 value, because f of 6.1 is way up here. So we're not going to get a 0 over 0 because the f of 6 isn't anywhere close to talking to f of 6.1. Usually f of 6 is close to f of 6.1, but in this case it's not. And again, that derivative, which is a limit, won't exist. So here are the 3 common ways to have a derivative fail to exist. Got a corner, got a vertical tangent line, or any old discontinuity, then we've got a problem. So moving to number 2, it says let's identify all points of non-differentiability of these functions. So part A, anybody know the name of this function? It's notation that kind of looks like absolute value, but it's different. It's not a very common function, so it's okay if you don't know what it is. Anybody know what it is? So I've seen this thing called the floor function, or the greatest integer function. What it means is whatever the input is, you take it and you round it down. So for example, f of 2.3, if I say take 2.3 and round it down, what do you get? 2. And if I said f of 2.9, you take 2.9 and you round it down and you get 2. So it's not round, it's round down. So what that means is that every number between 2 and 3 is going to get sent to 2. And so I think that's what these numbers are here. All of these numbers between 2 and 3 all get mapped to the number 2. So what do we think? Where is this function not differentiable? Do we have any corners to worry about? No. Do we have any vertical tangent lines to worry about? No. What's the only other thing to worry about? It's full of holes. Is any discontinuity? Where are the jumps for this function? Every whole number. And I think technically whole numbers are only the positives and zeros. So anybody know the fancy word for the whole numbers that include the negatives? It's not all reals. It's the integers. Good. So this function, non-differentiable at the integers, which we'll just write 0 and plus or minus 1 and plus or minus 2 forever. Okay, so any jump is a problem. Part B is apparently the 5th root of x function. What's the problem here? A vertical tangent line. Where? At x equals 0. So this function is differentiable every place except at x equals 0. All right, so there's our vertical tangent line. And then the last example here, part C, has 2 different rules. What's the name of a function that has more than one rule? Piecewise defined function. Okay, so the first function is just y equals x. Don't copy this because I need to erase stuff, but y equals x is just a line that goes perfectly through the first quadrant, right? So there's y equals x. But this rule only applies up until what number? 3. So then we got to stop it right when we get to 3. And at 3, are we putting in a filled in hole or an empty hole? Empty, because it says x is strictly less than 3. So you can copy that part if you want to. That's the first part. It turns out to still be there though. So there's the first part. And then the second part, 2x minus 3 is just another line, right? Slope is 2, y-intercept is negative 3. What we're going to do is plot that line, graph that line, by first finding where it starts. So for example, when the rules change at x equals 3, I got to know where this bottom line is. So 2 times the 3, 2 times x, minus the 3, happens to be 3. So I'm going to plot the point 3, 3, which will do what? It's going to fill in that circle. So just a coincidence. In most cases that would have stayed open, but happens to get filled in by the other rule. What's the slope of that bottom line? 2, right? Number in front of the x, mx plus b. So that means that if I rise 2, I should run 1. So there's another point that's on the line, and then you can just connect the dots. It goes that way. So where is this function not differentiable? At x equals 3. And what's the problem at that one point? It's a corner. Sometimes corners are more subtle than others, but there is definitely a change in slope at that point. Differentiable at x equals 3. Everywhere else it's fine. Okay, and then finally 3 is just a little bit of vocabulary. So you can say that a function is differentiable at x equals 2, or, so the arrows mean, these two phrases mean the same thing. You can just say it's differentiable at 2. So the x is kind of implied. If a function is differentiable on an entire interval, then you can say that. The function is differentiable on the interval from 0 to 5. And if a function is differentiable everywhere, like on all real numbers, then you can just say it's differentiable. The all real numbers part is implied. Okay, the rest of the demo starts on the next page. Some of these are going to be tougher, but in the first two, again, you are graphing the derivative of the function pictured.